Hello everybody and welcome to this seminar. I'm Morteza Haghir Chehreghani from Chalmers University of Technology. Today I'm going to talk about adaptive information acquisition and its use for sequential decision making in AI. This is a joint work with Yushin Chen from University of Chicago, Jean-Michel Renders from Naver Labs Europe, and Andreas Krause from ETH Zurich. Let's start with some examples. Assume that your cell phone is broken and you contact a call center or service center in order to find out the root cause of your broken device. There is an agent in this call center, which can be a virtual agent. Then the agent starts asking questions about the symptoms of your broken device. For example, the first question can be about SIM card, if it works or not. You provide an answer, and accordingly, the agent asks the second question, which can be, for example, about SMS delivery. And you provide an answer, and then the third question is asked, can be, for example, about internet connection, and so on. Until at the end, the agent tries to find the root cause for your broken device with a sufficient or minimal number of interactions and questions. Therefore, in this problem, we need to solve a sequential decision-making task where the goal is to compute an optimal testing policy. Optimal in this sense that we want to find the root cause with a minimal number of tests or interactions or questions. We can think of this kind of paradigm in many other applications and problems. For example, we can consider an intelligent medical system where its goal is to find out the cause or propose treatments to the patients. Then the system starts proposing medical tests in a sequential way where every new medical test depends on the outcomes and results of the previous tests. And we know that the medical tests can be expensive, so it is very important to perform this task and find out the root cause or propose a treatment in most efficient way. Another example is interactive recommendation. Assume you want to travel from Gothenburg to Stockholm. However, you might have some objections in mind. For example, you want to go first shopping, library, or other tasks, or you might have some preferences. For example, you prefer to avoid a traffic jam, and so on. Then the interactive recommendation system in your car starts asking questions about your preferences, and its goal is to find out and recommend the optimal desired path with a minimal number of interactions or interruptions. Another example is viral marketing. Assume a company has produced a new product or device and wants to do marketing over a social network. So the company offers this new product to some people for free in this social network in order to advertise it. So then the first user is selected and its impact or influence is investigated over this social network. And accordingly, the second user then is selected to receive this product. Again, the influence is investigated, and then the third one, and so on. The goal is to maximize the overall influence over this social network, and the process is done in a sequential way. We can think of many other applications and problems in different domains, such as optimal control, adaptive sensing, active learning, sequential, experimental design, decision analysis, operation research, and so on, where we need to adaptively collect and acquire the sufficient information in order to solve an underlying sequential decision-making task. Here, I start formulating the problem in more detail. In this setting, we are given a set of n tests with binary outcomes. For example, in the interactive troubleshooting, the tests can be, for example, about SMS delivery, connection to internet, and so on. Whenever we perform a test, it reveals some information about some hidden state or decision region shown by Y. I will explain later what it means. And it has some non-negative costs. In this formulation, we have also a hypothesis space which consists of the full realizations of all tests. If we have n tests, then we will have a hypothesis space of cardinality 2 to the power of n different members. So here you see a demonstration of this hypothesis space. Every point corresponds to one specific hypothesis, which is actually an n-dimensional vector, wherein each element corresponds to one specific test outcome. In addition, we have some hidden states or decision regions which are shown by y1 to yn. They correspond to these larger regions shown in this picture, and each of them consists of a subset of hypotheses, as you can see here, and they can be overlapping. And for time being, we assume that the conditional probabilities of test outcomes given root causes are given. So we use theta ij to show this, which corresponds to p of probability of xi conditioned on yj. And we assume that these probabilities are given. We use xt, capital XT, to refer to the random variable which corresponds to the outcome of test t, and small xt denotes the observed outcome. And we might have performed a subset of tests shown by script A. Then we use vector x to represent the outcomes. We also assume that the xi's, the different tests, are conditionally independent given the decision regions or hidden states. This means that the joint probability of p of y and x1 to xn can be written as p of y times the product of individual conditional probabilities p of xi conditioned on y. So here we assume, or we make naive Bayes assumption. Whenever we perform a new test, then a subset of hypotheses which are inconsistent with the outcome of the test are removed or eliminated. As you see here, for example, we have performed a test in interactive troubleshooting application, and the hypotheses which are at the left are inconsistent with the outcome, and they are removed. Then the task is to perform a sufficient number of tests or questions or interactions such that at the end we have only one single active decision region. So we reduce the uncertainty to only one single decision region. The other decision regions are removed out, as you see here. Then the goal is to compute an optimal policy for decision making for which the cost is minimal. This problem is sometimes called a decision region determination, and as I explained, the goal is to compute an optimal policy which leads to a minimal cost in average or expectation, under the constraint that all the remaining hypotheses are included in only one single region. This problem is NP hard in general, which means that in practice it is intractable. Therefore, in practice, usually adaptive greedy policies or adaptive greedy algorithms are used to solve this task. Assume we have performed 3 tests and we have seen the outcomes, as you see here. Then we define a quantity called conditional expected benefit for performing a new test, which depends on a definition of an objective function f. So this objective function specifies or measures the goodness or quality of a sequence of tests or a sequence of tests that are performed one after the other. So we can use this objective in order to measure the conditional expected benefit for performing a new test, which means in expectation how much benefit we can gain or we can achieve if we perform a new test. So this is computed for every new test. Then using this conditional expected benefits for the available new tests, we design the adaptive greedy algorithm. At the beginning, the set of performed tests is empty, and at every step we pick a new test which yields a maximal conditional expected benefit. Then we choose this test and we perform it, we observe the outcome, we add it to the set of available tests, and then we continue with the next test until at the end we have only one single decision region which is consistent with the test outcomes. So we reduce the uncertainty over only one single decision region. In the literature, there are several ways to quantify or choose this conditional expected benefit. For example, uncertainty sampling suggests to choose a new test at every step, which leads to a maximal reduction of the entropy over the hypothesis space. Then information gain suggests to choose a new test that leads to a maximal reduction of the entropy over the decision regions. And also it is possible to define some utility functions and try to maximize these utility functions at different steps. However, it is possible to show that all these approaches may require exponentially more tests than the optimal number of tests. In other words, the cost of this kind of greedy algorithm can be exponentially more compared to the cost of the optimal policy. Then the question is, when does the adaptive greedy policy work? When we can use it in practice? To address this, first I introduce some concepts. Let's assume that we have two subsets of tests called A and B, and we assume A is a subset of B, which means that the tests performed in A are already included in B, and the test outcomes are also consistent. Of course, there might be some tests present in B which might be absent in A. Then we call F adaptive submodular if for every new unperformed test like S, the conditional expected benefit of this test conditioned on XA is larger than or equal to the conditional expected benefit of this test conditioned on B. So informally, it means that if we condition on a smaller subset of performed tests, then the conditional expected benefit is larger. Then Golovin and Krause have shown that if f is adaptive monotone and adaptive submodular with respect to some underlying distribution p, then the greedy policy algorithm achieves a logarithmic factor approximation with respect to the best policy in terms of the expected cost. This means that the expected or average cost of the greedy algorithm is upper bounded by a logarithmic factor times the cost of the best policy. One popular choice that satisfies adaptive submodularity and we use in this work is equivalence class edge cutting, which works as following. It is also called EC2. Assume that we have three tests, T1, T2, and T3. And also there are three decision regions, as shown here by different colors, blue, green, and orange. Furthermore, we assume there are 5 hypotheses available at the moment in this problem. 2 belong to the green decision region, 2 belong to the orange decision region, and 1 belongs to the blue decision region. And using the parameters of the system, which are the conditional probabilities and P of y, we can use P of y and P of x i's conditions on yj. We can use them to compute probability for every available hypothesis, like P of h. Here, the size of the hypothesis or the size of the inner balls show the or correspond to the probability of the respective hypothesis. So a larger size indicates a higher probability for this specific hypothesis. Okay, so that's the setting that we have. Then EC2 first suggests to construct a graph where the nodes are the hypothesis. And in this graph, we consider an edge between every 2 hypotheses or nodes which are in different decision regions. For example, we do not establish an edge between the 2 hypotheses which are in the green decision region, and the same for the 2 hypotheses which are in the orange decision region. And this graph is weighted. So to compute the edge weights, we consider the probabilities assigned to the hypothesis at the 2 sides of the edges. And a particular edge weight is obtained by the product of the probabilities of the hypotheses which are at the 2 sides of the edge. And in this way, we obtain a weighted graph. Whenever we perform a test, for example, we perform T1 and we observe the outcome, which is 1, then we eliminate or remove a subset of inconsistent hypothesis and also the respective or connecting edge weights. For example, in this picture, we see that the hypotheses highlighted by gray are inconsistent with the outcome of T1. So they have to be eliminated. And if we eliminate them, we also eliminate or cut the edge weights which are involved in this hypothesis. Then EC2 objective works as following: that EC2 suggests that at each step we perform a new test which leads to a maximal cut or elimination of the edge weights over the graph. So at every step we build a graph according to the procedure that I described, and we can compute the expected removal or cut of the edge weight caused by each test, and we choose a test that leads to a maximal cut of the edge weights. EC2 looks an effective algorithm and provides strong theoretical guarantees. However, there are still several issues that in the following I will talk about them. The first issue is about computational aspects. All the methods that I mentioned, either EC2 or uncertainty sampling or information gain, they require explicit enumeration of the hypothesis space. If you remember, there are n different tests in the system, then the cardinality of the hypothesis space would be 2 to the power of n. However, enumeration of this number of hypotheses can be very inefficient or impossible in many cases. On the other hand, naive or MC sampling cannot be so useful here. Therefore, in order to address this issue, we have proposed an efficient dynamic hypothesis sampling scheme, where the idea is that we generate the most likely hypothesis for every decision region, and we apply the algorithms on this limited hypothesis space. Assume that we have m different decision regions shown by y1 to ym, and for each decision region we consider a frontier. And the task of this frontier is to generate the next most likely hypothesis or most probable hypothesis for the specific decision region. We do this for all decision regions, and then we obtain H tilde, which represents a limited hypothesis space. Then we can apply, for example, EC2 or uncertainty sampling or information gain on this limited hypothesis space to choose the next test. When the next test is selected, we can perform this test and we observe the outcome, and according to the outcome we eliminate a subset of hypotheses from this space which are inconsistent with the outcome of the test. Then we need to update the limited hypothesis space. So we call again these frontiers to generate new hypotheses for the decision regions that they have lost some of the hypotheses, if possible. Then we have again this limited hypothesis space. We apply EC2 or other algorithms, and we choose the next test. We perform it, and we remove another subset of hypotheses, and we continue this procedure until we reduce the uncertainty to one single decision region, which means that until at the end we have only one consistent or active decision region. We have a parameter here which is eta, and eta is kind of hyperparameter, and at each step when we do this dynamic hypothesis sampling, we try to cover up to 1 minus eta of the total mass of every decision region. For this sampling scheme combined with EC2, we have been able to compute theoretical guarantee on the performance. We have shown that the average cost of this EC2 method applied with this dynamic hypothesis sampling is upper bounded by this logarithmic factor times the cost of the optimal policy to be performed on the original hypothesis space. So far, we have assumed that the conditional probabilities of test outcomes given decision regions or root causes are given. So theta ij's, which correspond to P of xi conditioned on yj, are given. In some application, we might have access to some training data or some prior knowledge that we can use to estimate these parameters. However, in many applications, we might not have this information. So these are very critical parameters of this kind of problems, which might not be provided in advance. In the following, I describe an online learning paradigm to learn these parameters as long as we perform this task on different problem instances. Let's consider again the interactive troubleshooting task or problem. So in this problem, the virtual agent receives the first customer and starts asking questions about the symptoms until it finds out the root cause. Then the second customer arrives and is served by the virtual agent to find out the root cause, and then the third one, the fourth one, and so on. So we have kind of incremental or online paradigm where different customers are served by this virtual agent one after the other. Then we use this paradigm and we design an online learning of the parameters by adapting Thompson sampling or posterior sampling. Assume that at the beginning we have a prior distribution over the model parameters. For example, in this interactive troubleshooting, we may consider a beta prior over the theta parameters. So over every theta ij, we consider a beta distribution whose parameters are alpha ij and beta ij. Then at the beginning of each session, we sample theta ij's from this beta distribution. Then for this specific problem instance or for this specific customer, we run either EC2 or uncertainty sampling or information gain with dynamic hypothesis enumeration and sampling method in order to pick the test for this specific problem instance. When the session is over, then we observe YT, the decision region, and a set of test outcomes. Then we can use this information to update our estimates about the parameters of the beta distribution. In more detail, for the specific decision region, if the outcome of a test is yes, then we increase the alpha parameter of the respective beta distribution by 1, and if the outcome is 0, we increase the beta parameter of the beta distribution by 1. So in this way, we update the parameters of the beta distribution for the specific observations that we receive. Then for the next session or for next problem instance or customer, we sample the parameters theta ij's from the updated beta distribution, and we continue this procedure until at the end we hope that after a long enough number of problem instances or customers, then we will have a reliable estimation of the parameters. Here you see the pseudocode of the online framework that I described, that I don't go into detail. And for this online learning paradigm or framework, we have been able to obtain strong theoretical results in terms of average regret. Assume that tau is the maximal EC2 cost, which means if the costs are unit, which means the maximal number of tests that are performed in one specific session. And K is the number of customers. Then as K goes to infinity, when the K is large enough, then we show that the average regret of this online learning paradigm with EC2 is upper bounded by eta over tau. If you remember, eta is related to the coverage of different decision regions when we apply this dynamic hypothesis sampling. So at each step we aim to cover up to 1 minus eta of total mass. Now here I describe some experimental results. We have investigated and studied this framework and these methods on real-world application at Xerox Research, which is about interactive troubleshooting. In this application, we have 1100 root causes, and the number of tests is 950 with binary outcomes, which are about questions and symptoms, can be yes or no. And at the beginning, we assume that we can compute the conditional probabilities, theta ij. So we have access to training data that can be used to compute these parameters. And we investigate the methods on 10,000 different test scenarios, and we report the results. To evaluate the performance of different methods, we use this utility function here, which is proposed and suggested by an expert. So in this figure, you see the query complexity, which corresponds to the number of tests or questions as a function of the number of samples per root cause. The x-axis shows the number of samples or hypotheses per root cause or decision region, and the y-axis shows the number of questions or tests until we obtain or get only one single consistent decision region. And we observe that EC2 is more efficient compared to the alternatives. So EC2 enables us to find the decision region with less complexity or less interactions and questions. If we look at the utility here, we see that different methods are consistent. So in this result, we show the average utility as a function of the number of hypotheses or samples per root cause. And we observe that the different methods are consistent. So these two plus or results should be seen together. So from these two plus, we conclude that EC2 is able to achieve the same performance in terms of utility, but with lower complexity or lower interactions and questions. Then, in the following, we study the online learning paradigm. In this setting, we assume that we do not have access to the true parameters or correct parameters of the system, and we aim to learn them using this online paradigm. So the experiments here that are reported are in three different settings. The static setting corresponds to the case that we just use some initial guess for the unknown parameters. The full info setting corresponds to the case that we have access to the full information about the parameters. And the online VOI corresponds to the case that we learn the unknown parameters via the described procedure. And here you see some more detailed results. First, let's look at the right plots, which are about average utilities for different methods. Here we observe that different variants of online methods, either online information gain or online uncertainty sampling or online EC2, they yield consistent utilities. And as we perform more problem instances, the utility improves because we obtain more accurate and reliable estimation of the parameters. However, if we compare the results with the results at the left, which are about the complexities, we observe that online EC2 yields this good utility with much lower or less complexity compared to the alternatives. So the online EC2, in order to learn the parameters of the system and take the decision for every problem instant, requires or performs less interactions or questions or tests compared to uncertainty sampling and information gain. For more details and information about the results and also the theoretical aspects, you can have a look at this publication. Finally, I would like to emphasize that the proposed online learning paradigm is not limited to interactive troubleshooting application. We can use and adapt it for many different applications. For example, recently we have developed consistent and similar learning paradigms for online and energy efficient navigation of electric vehicles. In this problem, the task is to perform energy efficient navigation. However, the challenge is that the energy consumptions, for example, for different streets or roads, are unknown. To address this issue, we have developed an online learning paradigm where we learn the energy consumption, the unknown parameters of the system, along with optimization and navigation. So we use the current estimates of the parameters to perform optimization and navigation, and then based on the real observations and feedbacks, we update these parameters. This work has been done mainly by Niklas Åkerblom, and because of the time constraint, unfortunately, I cannot go into the detail. And I suggest, if you are interested, you can read more about this work at our very recent publication at ICHCAI. And a summary of results are shown here. And as we see here, the online learning paradigm based on Thompson sampling yields the minimal regret or maximal performance compared to the alternatives. Thank you very much. And if you have questions, I'm happy to answer.